Sorry, just give me 1 second. We'll start shortly. I just need to send out the YouTube link so that people who watch on YouTube can join. It's working now. Okay, I think we're good to go. Okay, cool. Let us start. So, stoichiometry, right? Very important. And in fact, I was just teaching the grade 12s, rate of reactions, and this carries over next year into rate of reactions, right? Your understanding of this section. Of course, it's important for like almost every part of chemistry that involves calculations, but there's a direct, like the things that you do in stoichiometry in grade 11, you will only directly see it again in rate of reactions, right? So like percentage yield, percentage purity, and all of that. Okay, so it's important. So far we went through the first formula, N is equal to M over M. Okay, I will be zooming in. I know there's an issue with the clear thing, and I know this is probably like not readable right now, but for the rest of it, I will be zooming in, and hopefully you guys will be able to see clearly. Okay, so N is equal to M over M. That's the formula we went through. We went through calculating the molar mass of something. Then we did percentage composition, okay, calculating the percentage composition of a certain element in a compound. Okay, then we did okay, just give me 2 seconds. Okay, sorry, I'm back. Okay, so yes, then we did N is equal to M over M, calculating molar mass, percentage composition, okay, different types of chemical formula. That wasn't so important. Then we discussed concentration. So the concentration formula, right? C is equal to N over V. Okay, we did some concentration calculations, right? You can use the mixed formula, or what I prefer to do is C is equal to N over V and N is equal to M over M, right? Knowing that, right? This is a key thing in this section, right? Knowing these formulas, like it might sound obvious, but knowing that if you have the mass, you can always get the moles. And if you have the moles, you can always get the mass because molar mass is always known from the periodic table, right? Then understanding C is equal to N over V, right? If you know the moles, you can get the concentration provided you know the volume. Okay, so you need to know moles and volume to get concentration, or you need to know concentration and moles to get volume, or concentration and volume to get moles. Okay, just understanding that C is equal to N over V, like sort of having it like memorized in your head what is contained in those formulas, so you know when you're dealing with a question what you can and cannot calculate. Okay, so that's important. So we did C is equal to N over V, some calculations with it. Then we discussed molar volumes of gases. Okay, so one thing to note, so we discussed STP, right, which is standard temperature and pressure. There is a standard temperature and pressure. Temperature is 0 degrees Celsius, pressure 1 atmospheric pressure, and the molar volume at STP is 22.4 decimeters cubed per mole to the negative 1. So that's the important thing we learned yesterday also, right? This whole concept of a mole. Okay, what is a mole? A mole is a standardized measurement that was created so that we can work with these values, okay? Because the amount of particles in certain compounds, even in small amounts of compounds or elements, the amount of particles they have is way too many to consider, okay? Or they are way too small to even consider, okay? So that's why they developed this mole concept, okay? And remember we said that 1 mole of anything is the same amount of particles as they are in 12 grams of carbon-12. So it's like some sort of standardized measurement where we're using carbon-12 as a reference point. Okay, again, all those details are not really important, right? What's important to us are calculations, but just a brief understanding of its background can help. Okay, just to remember it, or just having that brief thing is important, is kind of important as well. Okay, then we discussed what did we discuss here? Okay, percentage composition. Okay, then we discussed molar mass. Remember, we said that molar mass is the amount in grams that 1 mole of something is, right? How much it weighs, 1 mole. How many grams is it? Okay, so that comes back to, again, being 1 mole, because a single individual particle, it's too small to measure how much it weighs or what's its mass, right? Not weighs. Weighs is not the right term. Mass. What's its mass is more accurate. Okay, it's too small to consider what's its mass. So that's why that's what molar mass is, right? How much does what is the mass of 1 mole? Then we said concentration, right? Okay, and we discussed this molar volume concept, right? It's also this STP VM 22.4 is the volume of a gas at STP of 1 mole of a gas at STP. Okay, so again, using that standardized measurement here in molar volume as well. What's also important to note is sometimes it might not be STP. Okay, it might not be STP. It might be at 25 degrees Celsius, for example. Okay, in that case, right, they can give you a molar volume at a different temperature. Molar volume is just the mole, it's just the volume of 1 mole at that specific temperature. Okay, so if it's not at STP, right, they can give you the molar volume at a different temperature, and you just use the same formula. So N is equal to V over Vm, right? Let's just say at 25 degrees Celsius, okay, and they tell you that the molar volume at 25 degrees Celsius is, let's just say 24 decimeters cubed, not 22.4, it's 24, for example, all right? Then you'd use it, right? You'd substitute this also into the equation. Doesn't always have to be at STP, right? Provided that they give it to you, right? They give you the molar volume at that, or they could even ask you to calculate it, right? If you have the moles and the volume of something at a certain temperature, they could ask you, what's the molar volume at this temperature? You use this formula to calculate it. So just note, yesterday, I just want to clarify, I said that the only time you use this formula is at STP. It's not actually 100% true. You can use this formula at different temperatures. You just would have different molar volumes that you use, right? But if they mention STP, then yes, you're definitely using this formula, and you're using 22.4 or whatever they tell you to use at STP. Okay, so just keep that in mind. Example, a glass jar. Okay, we just did a basic volume calculation using these amounts, right? This was at STP, I think. Okay, at STP. Okay, so those are like basic concepts, right? Covered. Let's go through water of crystallization, which is kind of in like a weird place, but it's fine. We'll go through it. It's not too difficult. Okay, let's read. Okay, we have to go in like that. Water of crystallization. Some ionic crystals trap a certain number of water molecules between the ions as they are forming. These water molecules are known as water of crystallization. Example, hydrated copper sulfate, CuSO4.5H2O, has 5 water molecules per formula unit. When the hydrated salt crystals, when the hydrated salt crystals are heated, the water molecules evaporate off, leaving the anhydrous salt behind. Okay, so basically they're just evaporating this compound that has water in between its ions. Okay, and then the water falls off, right? Because if you evaporate something, you can reach it to the boiling point of water, and the water is going to evaporate off. All right, this is the chemical formula. So we have CuSO4 bonded to 5 water molecules, and then when you evaporate it, you have CuSO4 solid and the water as a gas, because it evaporated, right? Initially, the whole thing is a solid crystal, and then when you evaporate it, you can see that they now separate. Okay, initially they were bonded together, now they separate, okay, because they evaporated the water out. Okay, So to calculate, okay, the steps we'll go through after we actually do it practically. Just note the dot in the formula between the salt and the water means that a light bond is formed and not a multiplication dot. Okay, that's important. It just means there's a bond between the CuSO4 and the 5H2O. We're just going to quickly steal this equation. 1 second. Okay, there we go. Okay, so now that we've stolen that equation, let's work through this example. 1 second. I can have it in front of me and we can work through it. Okay, let's have a look at this example. They say that 13.2 grams of sample zinc sulfate, ZnSO4, and it's bonded to an X amount of water molecules. They were heated in a crucible. Calculate the number of moles of water of crystallization. So number of moles of water of crystallization is basically what number should be here. Okay, what is the moles? How many moles are there of H2O compared to the zinc sulfate? Okay, there's one zinc sulfate. How many moles of water are there? So the water of crystallization. If 7.4 grams, okay, of solid remained. Okay, so what's important to understand is the 7 point. So in this reaction, okay, so this is incorrect. Actually, we should have. Why they don't give us a reaction for this, man? Let's see. Yeah, that's fine for now. And let's get rid of this. Okay, that's okay as well. What is it? Zinc sulfate. Okay, let's look at ZnSO4 bonded to that. It's going to form ZnSO4 solid. Okay, plus H2O. So they are telling us, right, that 7.4 grams of solid remained behind. So that's this here. After it was, after the water was evaporated, 7.4 grams of solid, okay, was left behind. So the first thing that we have to calculate is what was the mass of H2O? Because the mass of H2O would tell us we can use the difference between the zinc sulfate, because we have the mass of the zinc sulfate. It's 13.2 grams. 13.2 grams of zinc sulfate initially was present. Okay, but then once we evaporated the water, once we got rid of the water, we were only left with 7.4 grams. So the difference between the two would tell us how much water actually evaporated. So the mass of H2O can be calculated using that concept. So mass of H2O, we can actually perhaps do this. 1 second. Okay, we can get the mass of, just want to make it bigger, okay, so that you guys can see it in case it's blurry. We need to use by calculating the difference between 13,2 and 7,4. So this is 13,2, this is 7,4 grams. So the difference would tell us how much water we have. Okay, so this is 13,2 grams. Okay, the difference would tell us that we have how much of water? We have 5,8 grams of water. Okay, it tells us that we have 5,8 grams of water. Okay, so now we have 5,8 grams of water. Okay, so now this is simple. right? The way that we compare these two, the way that we get this answer X is by comparing their moles. Okay, so we ultimately want to calculate the moles of ZnSO4 and the moles of H2O and compare them, and that would give us a ratio. 1:something, 1:something of H2O. Okay, so what we're going to do now, okay, is we're going to convert the masses of ZnSO4 and H2O. We're going to convert their masses to moles and then compare them. We're going to convert their masses to mole values and then compare them. So here, I'm going to calculate the moles of ZnSO4 by using M over big M, which is equal to, its mass is 7,4 divided by its molar mass. The molar mass of ZnSO4 is 161. When I do this calculation, I get ZnSO4's moles as 0,046 moles. Okay, and now I'm going to calculate the moles of H2O as well. Okay, the moles of H2O using M over molar mass. Okay, and how do I do this? I say is equal to, its mass is 5,8. So that's why we needed to calculate the mass of water, because we need to ultimately get its moles and compare it to the moles of ZnSO4. It's going to give us a ratio between the ZnSO4 and the water. Okay, so 5,8 divided by, what would this be? 16 plus 2, 18. And when we do this calculation, we get the moles of water as 0,32 moles. So the moles of ZnSO4 is 0,046, okay, and the moles of water is 0,32 moles. So that's ultimately what we want to calculate, right, in order to help us to get the moles of H2O, the moles of the water of crystallization, right? We want to convert the water and the ZnSO4 into moles. How do we do that? By getting, we have the mass of ZnSO4 because they tell us that 7.4 grams of solid remained afterwards. Now we subtracted that from 13,2 to get the mass of H2O that was evaporated, convert them both to moles using their molars, their mass and their molar ratios. We get them as a ratio. So what we can then do, okay, is compare them. Okay, we're going to compare them. We're going to put the moles of ZnSO4 over the moles of H2O, and this is going to give us a ratio between the two. Okay. Sorry, we'll compare them the other way around. I'll tell you why. Because we want to get a whole number, because there'll be more water molecules compared to ZnSO4. Our answer is not going to be exact to a perfect ratio, but we're going to get an approximate number. So the best way to get an approximate number in this case is to compare them the other way around. So I'm just going to rewrite them the other way around. Okay, comparing the water over the salt. Okay, that's generally what you're going to do. Compare the water over the salt. Okay, and you'll see why in a bit. Okay, compare this to the moles of ZnSO4. 0,32. So we basically, you see, because now we're dividing, we want to see how many times can 0,46 go into 0,32. That's how we do ratio, right? So that's why we put the bigger number on top, 0,32 divided by 0,046. Okay, and this is going to give us a better answer. So when you put this in your calculator, 0.32 divided by 0.046, okay, you get an answer of 6,956 5. So you're going to round this off to the nearest whole number, okay, which is approximately equal to 7. Okay, so there you got your ratio. You got your ratio as a. So remember, this would be this. Okay, this would be 6 comma, let's move this as well. Okay, 1 sec. This would be 6 comma 9 or whatever divided by 1. Okay, because obviously 0 comma 46 goes into itself once, and it goes into 0 comma 32 6.95657 times, which is approximately equal to 7 over 1. Okay, so the ratio, if you want to rewrite this as a ratio, which would be ideal, the ratio of H2O moles to the ratio of ZnSO4 moles, okay, is a ratio of 7 water molecules to 1 ZnSO4. Okay, sorry, I hope that that made sense and that that part of division didn't confuse you, right? Because it's the bigger one, you want to find out. This is similar to, you'll see when we do empirical formula and we divide it by the smallest moles, the smallest mole amount to get it into a ratio. So this is the exact same concept that we're doing. We're dividing the moles of water by the moles of ZnSO4, okay, to get a value for the ratio. Okay, we're comparing them as a ratio, and you will round off to the nearest whole number. So in this case, we'll get a 7:1 ratio, 7 in the favor of water. So for every one ZnSO4 that we have 7 water molecules, and therefore we solve for x. In the most questions, I'll say solve for x. So x is equal to 7. Okay, so you now round off to the nearest whole number, but sometimes if you get a whole number as well, and that's perfectly fine. Okay, if you're still confused or have any questions with that, please ask. Okay, but that's essentially how you solve this water of crystallization problem. Okay, and I hope you guys understand the concept, okay, of having the mass of the total salt with the water, okay, and then they tell you the mass of the solid afterwards or the salt afterwards, and then you can subtract them to get the mass of the water. Ideally, or like ultimately what you want is you want to convert them both to their moles. Okay, you cannot compare their masses because their moles would take into consideration the molar mass. So you're going to compare their moles and create a ratio with their moles. So there's 0.46 moles of ZnSO4 and there's 0.32 moles of water. Then you can compare them as a ratio. Okay, so when we actually did compare them, we found that there's approximately 7 times more water than there is of ZnSO4. That's how we got the ratio of 7:1. Okay, let's move on. Calculating the empirical formula of a compound from its mass. Okay, calculating it from percentage composition is the more common example, right? But we can do this as well, right? This is possible as well, calculating the empirical formula of a compound from the mass. So it says, to determine the mass, to calculate the empirical formula of a compound from mass, determine the mass of the elements, determine the mole of each substance, and simplify the atomic ratio. So it says, in a combustion reaction, 0.48 grams of magnesium ribbon is burnt. The amount of magnesium oxide produced is 0.8 grams. Calculate the empirical formula of magnesium oxide. Okay, that's fine. That works. Okay. So in a combustion reaction, right? Remember, combustion reaction is a reaction with oxygen. Okay. 0.48 grams of magnesium ribbon is burnt and 0.8 grams of magnesium oxide is formed. Okay. So with these amounts, 0.48 grams magnesium, and what is formed? 0.8 grams of MgO. So how much oxygen was used? You just have to say 0.8 minus 0.48 to tell us that 0.32 grams of oxygen was used. So when we combine 0.48, 0.32, we get 0.8. Okay, so they just gave the amount of magnesium oxide, so don't let that confuse you. But now we want to calculate the empirical formula. So remember the empirical formula, we defined it on the previous page somewhere. We said that the empirical formula is the simplest whole number ratio of the atoms. Okay, so that's what we're trying to determine. The ratio between the atoms, like how many magnesium is there to oxygen? Is it Mg50 and O23? Or is it Mg3, O2, Mg2, O1, Mg02? What is it, right? That's what we're trying to determine, the simplest whole number ratio between the two. Okay, so in this case, right, the steps here, we're going to follow the steps in this table very nicely, step by step, and pretend that we did not see the actual answer. Get rid of that. Okay, so let's go through this, right? So the first step is to determine the mass of the element. So we have 0.48 grams. And then for oxygen, we have to say 0.8 minus that 0.48 to get 0.32 grams, right? So because they gave the question definitely. They could have easily given the mass of oxygen as well, but now they gave the mass of the MgO. Okay, it's not too big of a train smash, but that's how we calculate it. Okay, now step 2 is to determine their mole. Okay, but by just dividing by the mass of 1 mole. Okay, the mass of 1 mole, remember, that's basically the molar mass, right? Because molar mass is the mass of 1 mole. So the mass of 1 mole, that's what they're saying here, divide by the mass of 1 mole, which is again essentially the molar mass. Okay, so you're just going to divide magnesium, its mass, by its molar mass, and the molar mass of just 1 mole. Okay, so even for example, oxygen is O2, right? Don't divide it by 16, don't divide it by 32, divide it by 16, just the mass of 1 mole. So magnesium is 24, so we get this as how many moles? 0.02 moles. Okay, and this guy here also, okay, so by the way, which formula did I use? I used N is equal to M over big M, right? And then here I will say 0.32 divided by 16, the molar mass of oxygen. And here I also get 0.02 moles. Now, generally, the next step is to divide by the smallest answer that you got. The smallest mole answer that you got here. You divide all of them by that. In this case, they're both the same. So you're going to divide them by one of them. So 0.2 divided by 0.2. This is 1. 0.02 divided by 0.02. This is 1. So the answer here is 1 to 1. The ratio is a 1 to 1 ratio. So the ratio is a 1 to 1 ratio. So the final empirical formula answer is indeed Mg, 1 Mg and 1 O. So it's Mg1O1, but we don't have to write those ones. The ratio is 1 to 1, so you just have MgO. Okay, let's do the next example. Now this is calculating empirical formula from percentage composition. Okay, let me see how. 1 second, I just want to see how clear things are looking. Okay, not too shabby. Okay, so calculating the empirical formula, okay, from percentage composition. Now, this is the more common example, right? The empirical formula of a compound can also be found from its percentage composition. We assume that 100 grams of the compound is analyzed, then each percentage gives the mass of the element in grams in 100 grams of the compound. So that's the concept behind it, right? We'll come back to that after we do the question. Maybe that will make more sense. So an oxide of sulfur contains 40% sulfur and 60% oxygen by mass. Determine the empirical formula of this oxide of sulfur. Okay. So what we do is, let's get all of these things. We'll write it in ourselves. So the first thing is to determine the percentage of the element. So they said that sulfur has 40%, and they said that oxygen has 60%. Now, all we need to do is treat the percentage as a mass. Okay, don't do anything else. Just treat the percentage as a mass. So if it's 40% of sulfur, we're going to say that the mass of sulfur is 40 grams, 60% of oxygen, we're going to say that the mass of oxygen is 60 grams. Okay, that's what you should always do with the percentage that you get. If the mass is whatever the percentage is, you treat it as a mass. So in fact, when you substitute it into the formula, because then the next step is to determine the moles, because it's same mass, moles, smallest ratio. It's just the extra step of percentage in this case, right? You're going to use which formula? N is equal to mass over molar mass, right? That's the formula you're going to use. And the mass that you're going to use is this 40%, which you treated as 40 grams. So it's going to become 40 divided by, what are we working with? Sulfur. So the molar ratio thingy is 20, the molar mass, excuse me. The molar mass is 20, so you get 1,25 moles. Okay. Then you treat oxygen as a mass as well. So you're going to use this formula, N is equal to M over big M, right? Then it's going to be 60 divided by 16. Okay, and here you get 3,75 moles. Okay, so we treated it as a mass, so we converted the percentage, use it as a mass, convert the mass to moles. That's exactly what we did. We converted the mass to moles. Now we at this last step. Now it's to determine the smallest molar ratio. So what you need to do is divide all of the ratios that you just obtained by the smallest ratio. So you're going to divide them all by 1,25 because that's the smallest between the two. So you're going to say 1,25 divided by 1,25, and of course here you're going to get an answer of 1. Okay, and here you're going to say 3,75 divided by 1,25 as well. All right, let's change this to red. Divided by 1,25 as well. And where are we? Here you're going to get, let's do it, 3.75 divided by 1.25. You get an answer of exactly 3. So now we know, because we divided, so we know that there's 1.25 moles of that and 3.75 moles of that. All right, this comes back to that same concept that we learned for the water of crystallization, right? You divide it by the smallest one. That's what we had to do in that case also to get a ratio between these two. Okay, so in this essentially, this is what has given us the ratio, divided by the smallest ratio. So we divided by the smallest mole amount and we got our answer. So here, as you can see, the answer is just spoiled. The empirical formula is SO3. So this 1S and 3 O's. This is the empirical formula. I don't even know how to spell. There we go. Okay, so that's how we determine the empirical formula, divided by the smallest one, and we'll get that ratio. Okay, let's have a look at this. I think it's another example. Empirical, okay, yeah, so let's just go revise this thing. Where it says that we assume that 100 grams of the compound is analyzed, then each percentage gives the mass. So yeah, so the reason we treat these as masses is because we just assume that 100 grams is used, and then 40 out of 100, that's 40 grams, and 60 grams. So it all works out, right? So that's the key thing there. Okay, so example, a sample of oxygen of an oxide of copper contains 8 grams of copper combined with 1 gram of oxygen. Find the empirical formula of the compound. So this is another example, right? So here they tell us straightforward that copper is 8 grams and oxygen is 1 gram. Okay, now we get the moles. So we say 8 divided by the molar mass of copper is 63,5. Okay, and here we get an answer of 0,126 moles. Okay, here we say 1 oxygen is 16, and by the way, the formula that I used here is N is equal to M over M. Okay, I divided that by 16, I get 0,0 0.0625 moles when I do that calculation. Now I divide them both by the smallest. Of course, the second one is the smallest. So here I'm going to say 0.0625 divided by what? 0.0625. And of course, I'm going to get an answer of 1. Here I say 0.126 divided by 0.0625. And I get an answer of, let's do this in our calculator, 0.0126, 0.126 divided by 0. Okay, I get an answer of 2.016. That's it. No dot, dot, dot. It's not an irrational. 0.216. So this one you can round off. Whenever you have like a digit, at least a 0 or like a 1 in the first decimal place, you can definitely round that off to the nearest whole number. You can round it off to the nearest whole number. So this is approximately equal to 2, and that's fine. Okay, so yeah, from that you can deduce that your empirical formula is going to be S2O1. So that's the empirical formula. Okay, and I hope that makes sense. So yes, that's 0 or 1 decimal place after that you can round off to the nearest whole number, and it's approximately equal to 1, and you get that answer S2O. Okay, so those are examples of empirical formula from percentage composition and from mass. Okay, I hope that makes sense, right? It's not too bad. Okay, let's have a look at this now. Empirical formula to molecular formula. So remember, empirical formula is the simplest whole number ratio, while molecular formula is the actual amount, right? It's the actual amount that we need for that compound. Okay, so for example, if a certain compound has a formula of C10H15, okay, meaning you need 10 carbons and you need 15 hydrogens to form this compound. This would be its empirical formula, which we can simplify to a ratio of C1:3. No, C2:3, C2H3, right? This is its simplest whole number ratio. Okay, but this is the actual amount. The molecular formula is the actual amount. This is molecular formula. Okay, and this is empirical formula. Okay, so yeah, that's the difference. Okay, keep that in mind. Right, so empirical to molecular. The empirical formula is the simplest whole number ratio of the atoms in a molecule. The molecular formula is the actual ratio of the atoms in a molecule. The molecular formula can be calculated from the empirical formula and the relative molecular mass. Steps to determine molecular formula. Determine the empirical formula if not given. Determine the molecular mass of the empirical formula. Determine the ratio between molecular formula and empirical formula, multiply the ratio to the empirical formula. Okay, let's do an example, and those steps will make more sense, right? So it says butane has the empirical formula CH2. The molecular mass of butene is 56 grams per mole. Determine the molecular formula of butene. Okay, butene has the empirical formula of CH2. So what you are essentially doing when you're converting from empirical formula to molecular formula, the simple conversion, okay, let's look at this, right? Okay, let's not look at that. Change your mind. Okay, the simple thing you are doing is you are comparing molar masses. Because it's super easy to compare because their molar masses will be in a ratio. Because we're increasing these compounds in a ratio, right? The molecular formula, the empirical formula, sorry, has to contain the same ratio as the molecular formula, right? Then their molecular masses would be in a ratio as well. So for example, right, let's get the molecular mass of CH2, right? The molecular mass of CH2, carbon is 12, plus 2 hydrogens is 2. The molecular mass is 14. Molecular mass of CH2 is 14. So 56 has to be a multiple of 15. Okay, and I'll show you why, right? So CH2 is the simplest whole number ratio, right? CH2 is the simplest whole number ratio. What if we increase that by 1? What if we had C2H4, right? It still holds the exact same ratio. Okay, we're talking, these are molar masses. I'll write that in a bit. We're still talking about the same ratio. It's just now empirical, no, not empirical. It's just now a molecular formula, right? An exact amount. This would have to be 28. Okay, we have C3H6. Okay, this would have to add 14. So 14 plus 14 plus 14. This would have to be 42. Okay, then we have C4H8, and this would have to be add another 14. This would have to be 56. Okay, these are molar ratio, molar masses, by the way. Molar mass, of course, moles per grams per mole. Okay, now you see, you can't forget that, because now grams per mole, you know that what? Don't you know that the molecular mass is actually just the mass of 1 mole? So now you'll remember its units, right? It's grams per mole. Okay, so as you can see that the molar mass, so firstly, these are molar masses, the red ones. Okay, these are molecular formulas, right? These three would be the molecular formulas. Okay, while this guy is the empirical formula. I'm just going to write EF. That's the empirical formula, right? So I'm not expecting you to write out each one until you get to the molecular formula. You can simply just divide them, right? So ultimately, what you want to say is you want to say the molecular mass of the actual compound, right? The actual molecular mass compared to like the empirical. So yeah, okay. Here's the thing here. They give it. They give like a formula. The ratio. Okay, you should say molecular formula mass, molecular formula, molar mass, that is, divided by empirical formula mass. Okay, and in this case, it's going to be 56 divided by 14, and this is going to give you an answer of 4. Okay, so what this should tell you is that the molecular compound is 4 times bigger, 4 times bigger than the empirical one. Okay, and all you need to do is you need to take your empirical formula and multiply each one by 2. C1H2, sorry, multiply each one by 4 times 4 times 4. Okay, and you're going to get your molecular mass of C4H8. And this is your answer. I know I did a lot of things for something that is so simple, but just to explain the concept. Okay, this is how you get the molecular formula. Okay, so what is it called? The empirical formula is the simplest whole number ratio, and the molecular formulas, they consist of the same ratio. So their molar masses have to be multiples of the whatever the molar mass of any molecular formula has to be a multiple of the empirical formula's molar mass. Okay, that's really important. And it can be seen here as well. But all you have to do is just say the molecular formula mass divided by the empirical formula mass. I don't know if that's how you spell empirical. I don't really care. It's not. It needs an I instead of an A, but no, it's okay. Empirical formula mass, you say 56 divided by 14, that gives you 4. So that tells you that your molecular mass, your molecular formula mass is 4 times bigger than your empirical formula. So you need 4 times the amount of each one. That's it. Okay. So then you multiply each subscript. You refer to these little numbers as subscripts. You multiply each subscript by 4, and you get C4H8 in this case. Okay, so that's how you go from empirical to molecular. Okay, let's see what they say here. Balanced chemical equation. Example, N2 gas plus 3H2 gas gives us 2NH3 gas. The balanced chemical equation is the recipe. It tells us the reactants used, that is nitrogen and hydrogen. the products, blah, 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 one molecule. Okay, I don't know what they're saying and I don't care. Okay, let's leave it at that. It's almost time, and we'll end up at early, right? Just because we ended on a good place, like empirical formula, molecular formula, and so you're starting a new concept in 4 minutes. Okay. Yeah, there is one more thing. If I do forget, please remind me. I want to discuss with you guys what happens when you see sometimes you get ugly numbers for, when you divide by the smallest whole number ratio, or when you divide by the smallest ratio, you get like ugly numbers. You don't get like, you get like 1,375. Then what do you do? Okay, I just want to discuss those concepts. So I'll do that in the next lesson as well. Maybe I'll try and find an example and then we'll do one more example and then I'll list the different things that you can do. Right, so just keep that in mind. But yeah, okay, so we'll end it there. So we ended empirical formula. Next time we come back, okay, we will discuss, I don't know, I'll try and look at I think they just look at the regular stoichiometric calculation there, but I think we need to discuss balancing chemical reactions, number one. General stoichiometry, by doing calculations in stoichiometry. So we maybe look at this thingy that they gave us here. We'll do that example. Balance some chemical equations. Look at this example, and then we discuss this guy, limiting reactants or limiting reagents. Please note that we'll be using a Rice table. So for those of you who don't use a Rice table, the Rice table is just the better way. It just makes more sense, right? It just makes things easy, concise to understand. So we'll be doing that. And then we have percentage purity and percentage yield, and we are done. We're probably going to have at least 2 more lessons on stoichiometry. So yeah, cool. I will see you guys next week then. If you guys do have any questions, please let me know. And with regards to any extra lessons or anything, I will keep you guys posted. But yeah, cool. Thank you guys so much for joining. Have a good rest of your week. Jazakallah khair. Assalamu alaikum.